Hi, in this new video, it is a good idea to go and talk about peripherals. Let's see if we can understand the concept of a basic microcontroller running not alone anymore, but with the help of some external hardware and devices, or external or internal. This time we will start in the easy way, and this means using an external peripheral, an LCD display, something like this that you buy and then you use because you have the opportunity to use the hardware device to connect it with some pins to the microprocessor, and at the same time to use the high-level C functions that accompany this electronic component that in itself is nothing but a dedicated processor, highly elaborated. So the objective in this tutorial, it is everything, you see, specify, plan, develop, and test everything like this in a single video that now we can speed up because it's just go and talk again using one of the previous examples, for example, the 4-bit serial transmitter, but now you see we will modify that. It's going to be the serial transmitter LCD with this extra addition. You see, we will add some pins so we can establish a handshaking with this electronic device that on the other side is modeled, you see, conveniently in our simulator Proteus. So that is going to speed up everything related to the building of applications using such, complex device. In itself is quite complex, but when you use it using the libraries, it's not that so, right? So let's see how it works. So let's talk this time about, in this P11, you see, about the peripheral liquid crystal display. And we will apply that to any one of the projects that we've been experimenting with. For example, the same 4-bit serial transmitter that we studied in P10. But now it's going to be modified so that it is possible to add a liquid crystal display to represent text messages. So let's go studying in some way the specifications, okay? It is that simple. You have this device now in mind, you buy it for a few euros. For example, that one, the LM032L, and a standard that is based in this Hitachi peripheral. You can study that, clicking on the links, you get the data sheets of these devices, but in some way what you've got is the device that can be attached. You see, you have connections, and this time you will have 7 wires to make this handshaking with the microcontroller, okay? And so any one of the projects that we've been studying, for example, the other BCD1 digit, can be added, can be modified to add an LCD to display values. For example, this time was the addition in BCD of a single digit, so let's represent the result in the LCD display. Or, for example, let's invent a timer, okay? So you have a timer previously designed as a tutorial in P10 or in any other lesson, and now the idea is to modify the basic timer with this LCD in mind. And the same with this project 2 here, the 4-bit serial transmitter that now will be renamed so that it will include the LCD, okay? So the symbol is as usual, okay? This is the symbol that we've been using all the time, okay? But now, you see, there is new peripheral, an LCD display, this type of peripheral. So it is an LM032L, 2 rows, 16 characters. So this is what you can represent. You have this first row and several characters on them, and this is nothing but, you see, an array of columns and rows of pixels. So some of them can be set high and some of them are left low, so you can represent a letter very well, like if it were a 7-segment display, but more complex. But in some way, the same idea of representing the message you like. This time, simple capital letters or any kind of ASCII, you see, symbol. Very well. So to do that, you have to think about the electronics of this, how many wires you need and which ones. And that is one thing that you have to add to your schema. For example, if you are solving this in Proteus, you have to take care of your schema to add these high shaking pins. But in the end, what is necessary is to be able to use, you see, this device conveniently from a high-level perspective. So let's make it simple. You may like to use, you see, high-level functions so that you can use the LCD in this simple way from your C program. For example, LCD put string. What kind of a string? So, for example, this direct message, some dots, a white space, and then some letters, some capital letters and some small letters that way. So just a message. So you are able to write a string of, okay, an array of ASCII characters, and 16 at a time, if you like, that way. And then you can replace that immediate string by a variable. Doesn't matter, okay? But you see, the idea is to make it easy. Not focusing on the electronics, but focusing all the attention on the use of high-level functions to make it extremely easy in some way, right? So you need some of these LCD-related functions to move the cursor, to place the cursor at the beginning of the row, and you know, this kind of LCD put a string, basically. That is all what you need in some way. So if you have understood the specifications, this time we will go faster. What goes next, as you know, here you have the learning materials. If you like to try that first with other projects, you are invited, okay? Here you are, for example, all the necessary stuff for running the other BCD 1-digit, but now with this extension, LCD. So you have the C code and the modification of the electronic schematic. And then you have this other example that will be taken the next day to introduce the timers. And let's talk about a fixed timer, but with an LCD as well. Okay, so what we have in mind, you see, is to use this device, and if it's possible, modeled in Proteus, because you see, it is going to be a lot simpler, I can tell you. You see, 3 wires for to connect that to 3 port outputs, so you can select the device, you can read and write, and then there is 4 additional ports that can be programmed as bidirectional to read and write data to the display. That way, so fortunately, we have this device modeled in Proteus, so we will use that just immediately, because you know the planning is that simple. Apart from the schematic, that is in some way that one, you see, you have to add that to your symbol. What goes next is to talk about the additional functions that you have to have in your hand to be able to compile correctly all this new project containing the LCD, okay? The new name, serial transmitter LCD, to make it different. And in this new unit, P11. And then you have to take with you not only the serial transmitter LCD and the serial transmitter hardware and the software, not only these, but the functions, the high-level functions supplied by the LCD, so that them all will configure this new project. And you can compile that again with 0 errors, because it is everything required is here. Okay. And finally, if you like, you can even download the experiment, download this application in one of the microchip developing boards to see it, how it works for real. Okay, no problem with that. So the planning is that simple. thinking about the location, thinking about carrying with you the extra and additional functions, header files and C files, along with your one, and then go and start developing, okay? Because that's the point. Perhaps the only thing that you have to go thinking is where to add these high-level instructions, okay? What I mean, where is that you are going to add these high-level instructions, in which place, okay? Well, that's it, you see? You better think about what kind of message you like to write and where exactly. For example, if you are in idle state, waiting for the start transmission pulse, this is because this may be as long as necessary. Here, it's a good place. In this state idle, this is a good place to print a message. So this is what you have to do. You see, the usual thing, marking the serial output line, the end of pulse or the end of transmission 0, and now in this state just print a message, so that when the machine initializes the transmission, you see, it goes like that. But when there is another location where is that interesting to print a message, for example, if the data has been completely transmitted, you may add now an extra state in this diagram, so you can print now an end message. So in some way, the P10 exercise, the P10 project, is modified slightly to allow you, you see, a new output. You see what we are talking here? Just a new output. You have the usual outputs and then another one, because you have to send here a message. For example, you have to write idle state in the screen. So to do that, you need, this is nothing but a new output, okay? Is that clear? You see, you have the typical outputs and now a new output, but this new output is referring to the LCD device. That is all, okay? The other transitions and the other states are pretty much the same. So this is an idea, just a message at the beginning of the transmission and a message at the end of transmission, so that then without any condition, you see, you jump automatically when this message is print, you go automatically to the idle, and so you print a new message again. Something like this, just to try, okay? Or you may say print, or no, you may say click start transmission, and then transmission ends, for example. Those may be the messages here in this application. So very well. If you know that, what goes next immediately is to put that into action, because fortunately you have the C and the hardware and the software. So the software, I mean the hardware, is going to look like this. You see, you have to make room in your schema with the new 7 wires, okay? The new 7 wires to interface this device, as we said before. And that's all, okay? And try, because you see, everything is in place. Let's see if this is going to work or not, right? So after the planning, let's just continue the tutorial developing the application and tasting it interactively at the same time with both windows, the hardware and the software. So let's save this hardware in the right location, okay? Save the link as in the right location, that is as usual CSD P11, and now let's invent a new folder such as serial transmitter with the LCD peripheral. So this is the location. So let's save the hardware here, and let's save as well the link, the software. So now if you are inspecting this new folder is clean and only contains two files, the two files of interest. And as usual, now you can inspect the hardware. Okay, you have your virtual environment to do that, so you can inspect your hardware because the Proteus opens immediately. It is defined like this. Clicking twice the file, you get what you want, and this is the example circuit. You see, it is the same circuit as before, but we have added here the LCD, so perhaps it is something missing here. Let's rename that, and in order to rename, you see, it is serial transmitter LCD. So this happens when you copy from a previous example. So let's update this name. You see, so go to the child sheet and take it all. You see, copy that all to the clipboard, go to the top, rename that thing serial transmitter LCD, and now go back to the child sheet that now is empty and paste from the clipboard this way. Okay, so this is what you've got here. That's the basic circuit, but now you see with some extra connections in the port D. So you see we are using the port D in some way, almost every single pin in this port. This one as well can be used later, the port 7 if you like, to switch on and off the power supply of this device, but this is not implemented now. But you have 3 ports used for the handshaking signals and the other 4 used for the data. That is the way it works. Okay, and the names and everything is taken from the microchip PIC developing board and from the library. So you better do it as it is here. Do not make any modifications, because in some way this is given to you and that make it simpler. Okay, so if this is what we have now, we can just go to the top and inspect something else. Here you have the previously orchestrated, you see the pulse generator to automate the sequence, the transmission sequence, the same bulb generator, the reset button and everything else, and now the LM032L device. Okay, just connect it this way. So if this is the hardware, what is missing now naturally is the software environment. So this is why you jump to the MP lab and start, as you clean everything that you have here and start a new project as usual. An embedded system, an embedded standalone system, and now what? Well, the same PIC18F4520, and next, and now the same compiler, and now a different position, a different location. You see, you go 2 levels above or whatever, you find the P11, and this is the location. So you copy the name, Control C, you open this location, you see P11, and now you paste the name and you add PRJ project, and the machine generates this new folder inside your project location, and you say finish. And now, okay, what is happening here is that you have this workbench completely empty, but already tailored for this PIC18. So now is the time to add the source file. Which one? An existing item, naturally. Which existing item? You see, it is 1 level above. So .c, you say select, okay. And that is the file that is associated now to this new experiment. It is here as a project file. So you see, you can inspect it just now. It opens in this window. And the difference now you see from the very beginning is that you see there is a mark here. The machine do not understand very well what is written here. For example, LCD header file. This is the standard I/O, the standard input-output header. This is included in the main C program, no problem. But what this one? LCD header. So you see, and it has to be in the same location where are the remaining files of the same project. So where is that file. Where is that file you see that is missing here coming from? Well, you go to the web as usual, and perhaps here that you have the zip, the complete zipped project. You can open this zip, just as the simplest way. You open this zip and you simply take with you the LCDC and the LCD header and the other function that is associated to this LCD. You Control-C that and you paste that in your project location. So now you have, you see, a multiple file project. Exactly. You have your top serial transmitter LCD that is accompanied by these 4 files. So the 5 of them becomes, along with the hardware, becomes the new project. So now that you have everything in place, you see P11 serial transmitter LCD and the 5 files of interest. Why? Because you see, you have a more complex project now. You have the classical microprocessor. The kernel of the device is yet the same microprocessor, but now you have to attach to this microprocessor and a very elaborated device, the LCD, that requires, you know, new functions. So you can use it properly and everything can be compiled correctly. So now what you have to do is to do that addition here, because the files exist. So go to the source file and add existing items. Let's add the C files this way, select. So you see you have now 3 C files, and at the same time if you go to the header file section and add existing items, and here it is, for example, the place where you can add the H, the header file. So you click that, and now and naturally, if you like, you can add here other files. This is for nothing, but there is not a problem. Just to take them all, you see, there is other important files. Naturally, there is other important files like the hardware, you see. So this may be also a part of the project, just for you to have a reference, like your own notes or your own pictures. So everything can be organized in this project browser. But you know what is of interest here is, as you see, the header files, the delay and this one, for example, is used here. So now you see the warning or the error has disappeared. So there is no more errors now in this program related to the files that you have to include in it. And then there is the 3 C files. So from now on, you can compile that for this target microcontroller. But remember, before doing that cleaning and building the main project, it is better to go and change the properties, because we like something very specific. We like to work with the C90, okay? And we like to generate a COF, so that we will connect that output file, the compilation result, to the Proteus and run them together. So we apply these 2 conditions, and now probably it is time for compiling this the usual way. So if everything is in place, you see, there is this project. As usual, you see this extra, and then you have all the time in the world, you see. You can study that example, and you see here, for example, that there is new stage. Okay, so you have the idle and the end message, where probably you know, LCD functions are included, you see. Remember that the init system includes this function, the LCD init. You copy that from this example or from the others, okay? And then in the state logic, you have the logic to switch from one state to the next, as usual. But you see the output. In the output logic, you see, as we are expecting here, in the idle, you are generating the typical outputs, the serial out and the end of transmission outputs. But you know now, if it's the time to do so, you are writing, for example, idle mode and push start transmission messages. Put the string, and you are using LCD home. This means that the cursor is going to be in line 1, position 0, and that way. Okay, you clear the LCD, so you see now the machine will understand these functions, and they have meaning because they are written somewhere. And where is that they are written? Probably in LCDC. So when you click here clear, you see, you can Control-Alt click to see where they are. So if you click here, the machine probably will find them. You see the definition of the clear, so you have the LCD cursor function, the clear, the put a character, the go to, the set the cursor to the right or the left, and so on and so forth, right? Functions like this and that, LCD data, and this is mainly what we are using all the time. You can write a comment, a single ASCII character, but you see we are using that thing, LCD put a string, to write a full array of characters in a single instruction. And that is going to take time, naturally, but doesn't matter. Now the point is that we can compile this and make it work. Okay, because I insist on this. You have the hardware already hardwired in your prototyping board, and you have the associated high-level functions that can be used in a very normal way in your code that you have inherited from previous experiments. So that is the point. You know very well what you want and where to place the new instructions. All right, so now it's a good time to compile it all this way and see the way it works. Perhaps you have a long list of warnings related to different variables, but in the end the machine is trying its best to get what you want, which is a successful build. So you see now the project is that larger. You see 1491 bytes of program memory, okay, because every single instruction here has to be translated into and disassembled into assembly code. So 4.6%, and then you have 15 data, you see, 15 bytes of data, RAM variables. So that is what you've got. So now it's time, for example, to see if this is working or not. So you go to the child sheet in your hardware, and now you associate, as usual, this just generated file. You see it's P11, serial transmitter, X, distribution, default, production, and now this time it is when we have generated this COF. Just today, just now. So you open that, and you go to you say, okay, you have 4 megahertz, you go to the top, and now it's time for investigating if this is working or not. You see, you can use a single click, or you can use this automation. You see, you can use this automation by means of an external pulse generator that is going to generate the start transmission pulses for you automatically. Because you see, this simple device is just an instrument. Remember, you have the possibility to input voltages, sine waveforms, pulses, and everything else. Okay, audio signals. That is not bad for go and experiment with electronics. So this time, let's run that. So let's run this machine this way. And well, the idea is, if this is working very well, so you see, you have the message, you have, as well as before, the 4 channels of this oscilloscope connected, and now you see it's manual, it's automated. You see, so you have automated pulses, so the oscilloscope is triggering, as you have seen in P10, automatically. But if you like, you go manual, you can do that. See, no more triggers, you see, just only the clock and no more triggers. So if you like to capture now the trigger that you are clicking with this button, start, you simply say one shot triggering function. You see, the source for this shot is the source A, that is related to the channel A, and the channel A is connected. You see, the channel A is connected to the start button. So now it's time for clicking the button and capturing the signal. Okay, like this. Very well. Okay, but you see how does it take? You click, And even if you click that thing that fast, doesn't matter. It takes, all this time. You have cursors, and for example, this clicking has been here for 200 milliseconds. All right. And naturally, in 200 milliseconds, you've been able to transmit the bits that you have in mind, okay? That thing. So it is working. And well, it's working as usual. That's important. So you can reset the machine anytime you like. So you see, you have your initial message here, because now it's time for you to pay attention to the LCD screen. All right, look at this. The LCD screen representing the messages that you've got printed in your code. All right. So essentially, you are printing this message now because this is the idle state. And you are printing another fast message. Well, another message that is deleted and cleaned very fast because it goes back again to the idle situation. And you can see that now when clicking. You see, if you click idle mode and transmission ends, but the transmission ends is that fast removed that you cannot even see that for 1 second. Doesn't matter, okay? Just this application is for showing you the way and how easy or how simple it is to introduce this complicated device into your applications. So naturally, this is perhaps in some way not very practical, but you know that here you can have micro ovens, vending machines, protocol analyzers, data converters and data loggers, thermometers. Anything that you have in mind may work with an LCD display to show messages to the user. So it's not bad, okay? That is the demonstration. Okay, and perhaps to go, testing something very specific, what is occurring to me now, it is the idea of how long does it take to run this writing, because you know that writing a single lidi is very fast. Perhaps in 1 microsecond you can do the job of writing a single lidi, and this is perhaps why you have these read and write functions in the main loop, because it takes almost no time, 1 microsecond. But what it is the idea of writing to a device like this? How fast is that thing of writing to a device like this? So this is something that you can check, okay? Going as usual, step by step. For example, you can go down and place your cursor, and well, let's see first of all if everything is working fine. It should be running step by step, and it should be executing one instruction at a time like this. So be sure that you see it is, I don't know, but it is difficult to move now the system. You see, it's an interrupt detected. Why so? Perhaps you have to go and clear all breakpoints and this way and run. And again, yeah, it is here the machine stuck in this interrupt service routine, and I don't know. Because because you see, what exactly? Why the machine do not go straight to the loop? So you have a problem here. You see, we should investigate that, but in some way we can do that later. Let's see if we are able to answer the question: how long does it take to execute a writing instruction? And in order to do that, you may like to place your cursor here. You see, LCD put string. So now you may run that, and when you click, this is executed. You see, because you have a message to print. Okay. So let's see how long does it take to do that. Okay, let's run and let's click. This is the interrupt, and now let's place. Let's run. You see, and what? So let's place the other breakpoint here. So you see the program will go running and will stop, will break here at the beginning of this LCD put string instruction, okay, and will continue working later and will stop in the next breakpoint, which is just, you see, you are just placing breakpoints for the duration of a single instruction. That looks like to be C naturally, but remember that this is not that easy. You have a lot of assembly instructions here to execute from one breakpoint to the next. So how long does it take? You see, you have a call to the function, and the function that is implemented in another region of the program memory. Okay, so this is what you've got. So let's run now and let's perform this measurement. You see the machine, let's do that instead of automatic manual. You see, it is going to be me who is going to click that thing. So now let's run that. Okay, let's run. So now it's the time when we will stop counting, and you see it's paused, and now let's click. So that's it. You see, I have skipped that. Let me do it again. Click to start the first breakpoint and click the next breakpoint. Now I see it is that number down there. You see, it takes 81 milliseconds to write this instruction. You see, so this is really a lot of time. Look at this. This is the measurement that I like to perform. You see, it has taken 81.36. You see, 7 milliseconds. You see, remember, this is a 7 microseconds. So you see, 7 microseconds, but it has taken 81.3 milliseconds, all that time, 81,367 microseconds to execute this single instruction here. And this is something that you have to consider carefully in your applications, right? Probably the other one, LCD home, sending, not writing, but sending the cursor of this LCD to the first memory position. You see, to the first memory position. This is the idea of LCD home. This is what it means. It's going to be faster, but doesn't matter. You see, the important thing here is that writing this message takes about 81 milliseconds. All right, and that is a lot of time. So this device is all right, but it is a slow peripheral. It is quite slow compared with writing LEDs, for example. It is very slow. So what is that we can do here? Besides, is that we have to go writing once and again in the main loop? It's not so, right? So it is a lot better if we write only when this flag is set. And when this flag is going to be set for writing something into the screen that takes that much time? Well, when there is new information to write, you see? So now that this thing has been executed, we clear the flag. Okay? We clear the flag. And we will hold this flag 0, so that the next time that you are executing in the main loop the output logic, and it happens that you are yet again another time in the idle, this code will be skipped. You see, you will not execute that because the flag will be held 0. So this runs only one time, okay? Because there is no new information to write. Because the information, you see, the idle mode is already here, okay? Look at this, you have this just executed now, a single line, while the other line is clean, okay? That way. So because the program is just active, you see, now you have LCD home 2, you can execute that in a single instruction, you see? The cursor has moved to this new position, right? At the beginning of this second row, and now if you execute this function, you see, LCD put string, you in a single step skipping over this, you click and now the message appears, you see, and again a similar time has elapsed. You can measure that using breakpoints. So this is the way you can go experimenting. And as I say, you see, if you clean them all, you clear all the breakpoints, you go to the next message to print, and that happens down there, you see, in the end message. Okay. You have this idea of writing again a transmission end. Okay, so here you will find that this LCD flag is 1 again. Okay, because you have a new message to print. So in some way you have set this flag high somewhere in the code. Is that right? For example, here you have set that the bar LCD flag is going to be 1 because you have a new message to print. All right? When arriving to the end message state. Look at this. You have here the idea of setting this flag again because in the end message state, you see, in the end message state, you like to print this new end of transmission message. That is the way it works. All right. So this code is executed when arriving for the first time at this end message state, and only once, because what you say after this, well, in this application, what you keep this flag high because you go back to the idle and you need this flag high to reprint on arrival to the idle state again this new message. So in some way you have here 2 consecutive messages, and one of them it is here as long as you are not clicking the start button, and the other it takes only 200 milliseconds. So this is why you see the second message that short of time, transmission end. Okay, that short. So well, go in your way, practicing as much as you like. All right.